Um, hi, can you hear me? No? Hi, is it okay? So, so today's goal is to finish this dynamic games of complete information. So, this part have actually two set of topic. One is the general dynamic complete game, where each stage is likely to be different from the other stage. Okay, and we'll focus on a special case, which is called repeated game, which is have a very important applications because it talk about if you repeat the game many times, are you going to able to deliver something very different? So one of the main idea of repeated game, which we'll talk about second of this class, is what we call the Fock theorem, which means that even though precedent dynamic, the effect is the outcome we predict. If you allow the game to be repeated many times, actually you need infinite many times, and that the things become very different. Okay, so if you expect the collaboration is going to continue long enough, or you don't expect there's some termination date, then things will be very different. Okay, so that is the ideal collaboration, right? If you are not expected to interact with your friend in the future, and we're likely that things will be very different. Okay, so but let's get started. So first, I just want to repeat what has been done last time quickly, and maybe it's good to compare to the previous chapter. We focus on the normal form game. The normal form game, if you remember, okay, we need to specify three things. First is who are the players, and who is the actions, just the study set, or what is the payoff, right? So basically, the three things is sufficient to pin down the whole interaction situations, right? Because there's no time dimension here. So what we are doing now is to put time into this framework, okay? Although we don't say time here, okay? It doesn't mean that static doesn't mean that there's no time dimension. It just means that when player making decision in the normal form game, they don't know what others are doing. Okay, when they make decision, it's just like under the uncertainty, you don't know actually what other action has been taken by the other firm, so the other opponent. Okay, so dynamic games of complete information, as you would expect, is at least for now, is we don't have every point of time. Every player has a complete picture of what's going on. Okay, and as we argue in the last class, it will be very different, right? Suppose you play rock, paper, and scissors with your friend. If you are doing simultaneous thing, right, it's very different from you doing sequential, right? If you sequential, the one who moves last will always win, right? The reason is being that your strategy, if you're the last mover, you will make decision according to what has chosen by the other guy, right? So your strategy is not simply a strategy. Your strategy simply have to depends on other people's strategy. So it's not just an action, but it's an action dependent on other people's action. So it's a function, right? So your choice is not just your action, but it's a function that your action contingent or conditional on others. Okay, so that is very complicated. Okay, and so to be sure, this although looks very simple, although we have complete information, and actually this is enough for many applications. So actually for me to make a living, I just rely on this game. Okay, I don't then ever go into incomplete information, and in most of my papers. Okay, there's some paper I go into that, but otherwise, many of my work actually IO work or apply, just basically focus on complete information is sufficient. I mean, unless you think your model have the reason why information asymmetry is important, right? Which is important in finance, right? But otherwise, in many scenario, incomplete information is not an issue to your problem. Okay, of course, then it may be important, but may not be central to your issue, right? So you can safely ignore those, right? That's why we look at Conrad or Bertrand. Is it the case that we assume firm have complete information, right? No, right? Is the idea that information will be in the long run will be there is not important. Right? Same as Conrad and Bertrand, right? Although we talk about static game, we don't talk about dynamic, right? But you can imagine if you, I mean, I don't provide the foundation, but indeed, actually, you can show if people following some dynamic playing, you will also end up in those kind of scenario. But anyway, here is what we said is dynamic game of community is you have to depend on what's playing, right? So the difference is before is H and T, but is now H and T depends on what are the bit chosen. And as I said, we discussed last class, and to describe the game, okay, you have to has much more complicated. Okay, so you can see the player set the same. Okay, the payoff function also the same. Okay, and one of the difference about the payoff function is not from the strategy profile to the payoff. Okay, I mean it's still the Z is the terminal node. It's still decided by what people's move before, but this is how we define. We only define at the terminal. Okay, Z is terminal node, and here we have to define what are the history. So which is what are the possible things can be done in the history, right? This is basically just H is coming from all the action has been done in the past. Okay, and do note that this is a complicated object. Okay, because it has all possible combination can be done. Okay, basically just all possible action can be taken by people in the sequence. Okay, and then player function tells who can move. Okay, so let's consider this again because I want you to know we're sure what is the definition, although you will never explicitly write down in your model. As I said, I have seen no paper actually write down this thing. Okay, but you have to be careful. You have to well specify every single thing, at least in your mind. You don't have to write it down, but you have to be very careful write down to make sure that there's no gap. Okay, in the model. Okay, because you will not aware. Because when you write, maybe some agent he do something. Okay, it's optimal to do, but you may forget the corner solution. What if the price charge too high? Is it still buying or not? Okay, you have to be very careful, even though you may not be aware of those. Okay, here we have player set is 1 and 2, and here history, as I said, history is what can be done in the past, right? So it can be the beginning that nothing can be done. Okay, and the time 1, player 1 can choose head or tail, so the history can be either head or tail. And player 2, after player 1 has chosen head or tail, he can choose head or tail. So the history can be head, tail, tail, head, tail, tail. So the terminal node is the 4 element, right? And the set of history is just like many things there, right? So that would be I mean, the reason why you need that because you need to decide the payoff for the Z, right? Okay, because you have to make sure that you have well-defined utility for each possible terminal history. So that is very important. I mean, because sometimes you would specify the model, and you may forget to define some of the history, and as you know, I mean, if you try to write a model, the most difficult part is where it's not the main thing, it's all the corner and minor thing. Okay, it's like math. I mean, if you do math, you know what I mean. The main thing is easy to prove. Usually, it's all the corner special case makes the things complicated. Same when you do game theory, right? It's like usually it's easy to characterize, find the equilibrium for most of the case, but for special case or generic parameters, then things become more complicated. and then look like this, and some of the notes can be difficult to handle. But anyway, and one of the good things about writing a model for business journal sometimes is you can safely ignore those. Usually you say, okay, I will focus on this set of parameter that I can find equilibrium, or I can find things that is reasonable, and that will be you should also do it when you write your model. Okay, and so the player function is decided under what history, non-terminal history, who is going to move, right? The beginning one move, after the first history, player 2 move. Okay, and you tell them what are the available actions, and here we focus on the case only one agent can move at a point of time, so that's why I don't have a agent here, right? So just action is just because only one guy is moving, and here after the terminal history, I will pay off. Okay, so as we said also last time, everything can be written in this diagram, right? Because what have been said is actually can be done here, right? So it's a tree diagram where you start in this game, you start with one guy, right? Start moving, and then this second guy or first guy also can be, but anyone who move in the second row, and then choose the action, and you can see the terminal the hollow, and the non-terminal are the black one, and after the terminal, then you have the payoff. Okay, so that is the idea here. Okay, and if you remember the Nash equilibrium in this game, is there's no pure strategy Nash equilibrium, right? Because remember the game, right? The game here is player 1 would lose $1 if they have the same size of the coin. If different, player 2 win, right? So player 2 always want to show different side of the coin, right? Because it will not randomize, right? If you're sequential, right? If they do the same time, then you randomize. Just imagine rock, paper, scissors, right? You would, if you do it same time, you randomize. But if your opponent you do the rock, paper, scissors, right? If you do sequential, you're the second guy to come out, you would of course see what he's doing. You do the winning strategy, right? So you would not commit at the beginning what you should do, right? What you should do should depend on what the other guy had done, right? So it is no longer reasonable to assume a mixed strategy. Okay, the reason is the commitment to randomize is not credible, it's not reasonable, it's no longer a smart thing to do, right? If I can have a machine, I press a button, okay, and that will randomize. Okay, that's fine. Okay, I can commit to that. I'm not going to move. I go out, drinking coffee. It's still a Nash equilibrium. But the thing that you can regret, if you can regret, then it is not going to be equilibrium, right? Because I say, let's play rock, paper, scissors. Okay, you go first, I go second. Okay, I claim I just randomized. Will you believe me? Right? The answer is, if you believe me, fine. Okay, but usually you will not. If you see what has been done for the other guy, you cannot commit, right? So that is a problem. Okay, the commitment is an issue. Or actually, if everyone, I don't know, everyone learn macro, and macro, there's a problem of central banking. Is the reason the central banker would not like to raise the interest rate, right? Because one of the goals of the central banker is raise the interest rate to fight inflation, right? But raise interest rate is harmful for economic activity, right? But the central bank cannot commit not to print the money, right? He cannot resist the temptation to secretly print the money, right? So that's why It's very hard. Okay, it's very hard. So that's why kind of commitment is a problem there. But anyway, as I said, if you know player one knows he choose head, he will choose tail, right? He choose head, right? Because he should say, right? Choose tail, then he will choose tail, right? Because player two would have a winning strategy by matching the pennies, right? So in order to for him to win, it's very simple, right? He will not randomize. Okay. So that's why from this kind of game, it suggests that Nash equilibrium is not a good outcome. Okay, it's not a good prediction when people interact dynamically. Okay, so how can we solve this problem? Okay, I think it's good to look at this problem. Actually, this is also a famous problem about in IO. It's all what we call the prediction game. It's where there's an entrant, okay, want to enter the industry, okay, and the action in the first stage is decide whether in or out, okay, and the incumbent will decide whether fight or you accommodate, right? If in, right? If out, then you don't need to do anything, right? Because the game ends, right? So so let's see the payoff, okay? If no entry, entrance stay outside, earn nothing. Player two, the incumbent, okay, actually earn $2 profit, okay. And if accommodate, they will share the $2, right? So the market worth $2, right? If like this, okay. But if they fight, okay, turn out to be they fight, they just burn the surplus, okay. They lose actually $4, okay. And the new guy lost more than the existing guy, okay. So that's the payoff. Okay, then you can actually write down this into the following matrix, right? If stay out, right? There's no need for him to choose, and then he'll get $2 the whole market, right? If they're peaceful, they split the $1. If they fight, the new guy and lose for $3. This is lose $1 for the old guy. Okay, so this is a very standard strategic entry model. Okay, and actually this idea is very simple, right? Just you can change the number, just like the out earn more than the accommodate, and which more than the fight, right? This is a standard model there. Okay, and the question would be, what would be the Nash equilibrium in this game? So let's do it together and see if you able to see which one's Nash equilibrium. Okay. Let's try to look at because only two outcome, you can just pick up the best response, right? Because remember, what's the Nash equilibrium? Is pick up the mutual best response. Okay. So consider the entrant. Look at the fight. Okay. If incumbent choose fight, what is the best response for entrant, right? What you do is compare 0 and -3, right? Then 0 is the better, right? So 0 is the best response for entrant facing fight. Okay, so if you want to write in that manner, will be entrant, okay, fight, it's just out. Okay, so that is what I mean. Underline, I just mean this best response. Okay, and if it's here, okay, maybe use other color to make it look more. If accommodate, so the best response will be in, right? Just to be exact, it will be like this. Accommodate will be in. Okay. Now we have done for the entrant, look at incumbent, right? Facing out, the incumbent actually have two best response, will be this and this. Okay. So which means that if you write incumbent facing out, actually it's a set. It's not a one guy, have to be fight and accommodate. Okay. Accommodate, sorry. Okay. And if you look at the sorry, the color, the green color, if in, okay, you compare -1 to 1, then it's accommodate. All right. And you can check or just look at the matrix. You can see actually there's two outcomes that have been the fixed point, right? This is the fixed point because it's mapped to itself, right? Or what we call, this is the mutual best response. These two, okay? So here we have two Nash equilibrium or Nash equilibria, if you want to be exact for the pronoun, equilibria or equilibriums, depends on whether you like which one. And the two equilibrias or equilibrium, and which one is you think is more reasonable, okay? And people would argue that, okay, this one is rather unreasonable, okay? The reason is being that if it's in, actually it's in, okay, you would choose to accommodate, right? So if you consider a case where ask ourselves, consider we're in the second stage, the entrant has entered. Would you accommodate or not? Okay. If you accommodate, you get 1. If you fight, -1. Okay. So it is not really there, right? So it should be, this is appropriate, this is not. Can you see this? Can you see why this is not? Let me repeat. Okay. This one is not right because the entrant move first. Okay. Now consider the case entrant actually move. Okay, actually move in. Okay. Would you be fight or accommodate? Right. Actually, you would be accommodate, right? If you accommodate, which means that for the entrant, he have the choice of choosing 0 or 1. Right? Because you can actually pick. They will pick the second one. Because the entrant can actually pick which equilibrium will arise. Right? If he stay out, actually it's 0. But he go in is 1. So the reason is he moved first. He actually, in some sense, can choose which equilibrium can arise. Is that clear? Of course, if you stay out, yeah, that can be equilibrium. But if he go in, actually this will realize, right? So he can decide which outcome actually comes out. Okay. And is that clear what's going on? Okay. And this is optimal because right, you worry about when come in that will fight, right? Okay, let me talk about this. Okay, so and how does this related to game theory? How can we formalize the idea? Is what we call the belt induction that borrow from decision science. Okay, So basically, you, instead of looking at the problem from forward to the end of the game, which is usually the time evolved, okay, you do what we call backward induction. Okay, this is a decision-making process where you look at the very last stage of the problem and go back. Okay, and this backward induction idea is look at from the very last decision-making process. What you would do? Okay, decide, fight, accommodate. You would be doing accommodate, right? Because this negative is 1. So this is not relevant. Okay, and you put this to here. Okay, that will come up. That will come up into basically just this is better. Okay, then you just forget about this. Okay, and you move this to here. Okay, that is called backward induction. And and so if you cancel this out, right? And that means this is 1, 1 here. Okay, and player 2 will decide whether he would choose 0 or 1, right? He will choose 1. So that's why this is the unique prediction. Okay, if there's no equilibrium, this is only simple backward induction. Okay, there's no equilibrium. And what have been shown, okay, is the following. Okay, if we will have an idea we call subgame perfect equilibrium, or some people call subgame perfect Nash equilibrium. What it said is we will divide the game tree into a smaller component, okay, which called subgame. Okay, and subgame is it's a tree that you can stand by itself. Okay, and turn out to be, if you require every game is being a Nash equilibrium, okay, and that is same as backward induction. The idea is, okay, being that in this case, this become a one-person game. Okay, although it's not, it's a trivial case, but his best response is just this guy, right? And go back to here, okay, and subgame perfect require this shows this. Okay, so that's why you go back to here. Okay, this is not a subgame perfect equilibrium. The reason is this is not an equilibrium in that small game. Okay, so that's why this is removed. Okay, but I will talk about more about that. But this is how you find subgame perfect equilibrium. Is look at backward induction. Look at last stage. You find the Nash equilibrium. Plug in the outcome. Go back to the previous stage, and go on. But don't worry, we'll talk about this more. Okay. Before we go ahead, okay, let's do it together. Okay. What are the strategy set of player 1 and player 2? Player 1 have two strategy set. Sorry, set two strategy is A and B. Okay, let me write that down here. Okay, because you can only choose A and B. Okay, so his strategy is just A and B. Right? So look at player 2. Okay, player 2 is a little bit trickier. Okay, player 2 he has two choice. Okay, so the choice have to involve of if one choose A, what will be chosen? If choose B, what will be chosen? Okay, it will be he has to choose the following. Okay, it will be the set will be just he have to choose C, D, or E. Okay, and a cross product of F and G. So he have to choose C, D, E, one of them, and F and G, right? Say a typical strategy of say small s of 2. Okay. An example can be, say, C and F. Okay. Or another case can be D and F. Right. So in total, he has 6 strategy. Okay. Is that clear? Because you have to choose action for, specify for what happened in all the scenario. Okay. So it looks trivial, have to be very important. Have to make sure that for every single cases, okay, you have to specify what to be done. Okay. There should not be a case that we don't know what to do. Okay. You have to specify every possible case, even though it's impossible. Okay. So the next one is how many subgames in this game. Okay. So so the whole game usually we define is also a subgame. Okay. And actually there's some terminology I have to talk. I mean, it's very technical. So sometimes they call a proper subgame or subgame. Okay. And usually this is the whole game, it's a subgame, but it's not a proper subgame. Okay. And proper means a strictly smaller sometimes, right? And here we have a subgame. This is one subgame, right? Because player 2 is making a decision here, right? You can write down as a normal form game, or you write down as the game by itself, right? Here is also another game. Okay, so you can say here we have 3 subgames. Let me repeat. This one, and the whole one. Okay, so there are 3 situations. Okay, and what are the set of SPE? So you find all the subgame perfect equilibrium. Okay, so we will use the idea called bulk induction. Okay, so we will find all the next equilibrium in all subgame, and then we find it. Okay, so let's look at the first subgame. Let me look at the first subgame here. So player 2 payoff is 2, -1, 2. So what are the best response? Is C and E. Yes. Okay, so the best response have 2. Okay, so do note they have 2 best response. Usually that's how you write. Okay, you have arrow there. So there's a multiple equilibrium in the stage 2. Okay, there are 2 equilibrium in this subgame. And look at the other subgame. I use orange color. Oh no, the brown color. What is the next equilibrium here? Is G, right? Now, so because of there are multiple equilibrium here, okay, so it means that you need to consider 2 situations. Okay, let's consider first situation here. Let's forget about E. Okay, we have C here. Okay, if C here, look at player 1. Okay, player 1 is comparing 1 and 1, right? So both of them are okay. So both of them are best response. Okay, so that means that our first subgame perfect next equilibrium is A, okay, and CG, okay, is that's how you write. You write down the strategy. Okay, player 1 choose A, player 2 strategy is C, and G is our first subgame perfect next equilibrium. Is that clear? But also can choose B, C, G is also fine, right? So that means that we're another one. So the second one is B, C, and G. Okay. So do remind yourself that you need to tell me this. Okay, this is Nash equilibrium, but when you have AC and G, the outcome is AC, right? This is outcome. This outcome. This is sometimes we call Nash or subgame perfect Nash. It will be the equilibrium outcome. Just make sure that you have to distinguish this equilibrium outcome. This is equilibrium. Okay. Equilibrium is have to write down the complete strategy. Okay. Outcome you can just ignore. Just focus on the last thing. Okay. So, and here you can BG is actually comes out is B and G, right? Actually, the outcome is BG. Okay. And we have done the case where player 2 choose C here, right? What happens if player 2 choose E? If player 2 choose E, player 1 is choosing between 0 or 1, right? So B will be chosen. So BEG is a other subgame perfect Nash equilibrium. So it will be BEG. Okay. And when it's BG is outcome is also a BG. Okay. So you can see to support BG, okay, what we say, to support this outcome, actually you have two different kind of strategy can support the same thing. Okay. So that is a have to be careful, right? Sometimes you have a game where the outcome is unique, but then many strategy lead to the same outcome. Okay. Right, just like, okay, so that would be is that okay? Because just like the sequential matching pennies, right? No matter what the other guy do, okay, the second guy will match, right? The outcome, the payoff is the same. Always negative. Is always the guy doing the second will always win. Okay, the payoff is actually the same, right? So there's actually the three things have to be careful. First is whether the strategy can compare whether it's unique. The second is outcome. The third is payoff. Is that clear? Okay, the three thing here. There's a three thing that people you have to be careful about the complexity of description of the outcome. First, you can describe whether the strategy, or what we call the equilibrium, in fact, right? Is the equilibrium, okay? It's the most complex one, right? Because different equilibrium can lead to same outcome. Okay. So that means the second layer is the outcome. But different outcome can also do the same payoff. Okay. So that's why you have to describe actually the three layers of structure you need to describe the game. Okay. And it is possible even though you have multiple equilibrium, multiple outcome, man, payoff can be same. Okay. Then you still have a unique prediction. Right? Say matching pennies, sequential matching pennies, or you can think sequential rock, paper, and scissors. Okay. You are clear, you always clear that the second guy is going to lose $1, right? If the winning $1, right? If draw is 0, you always the guy who moves second always lose $1, right? It's a unique outcome, but it's unique in terms of payoff, right? Although it's not unique in outcome, right? But is that okay? So that yeah. BDG. Yeah, but D here is not it's not something that two we chose. Okay, that's good. That is the Nash equilibrium, but that's not the subgame perfect Nash equilibrium. Subgame perfect Nash equilibrium requires if, okay, you will say you never end up here, right? But we need to check if, okay, he shows here, is it going to be optimal? Okay, so that is the main idea of the subgame perfect is you have to, although you never end up there, you to make sure that this is going to be correct. This is the idea of what we said, the incumbent story, right? The entrance story is, right? You are actually choosing D, it's because he has chosen B, right? But is it reasonable for him to choose B because he moved first? He can decide where he's going. And if you ever go to here, you're not going to choose this one. So you claim you're choosing D is not credible. I don't believe you do this. If I actually choose D, you actually go to C and E, right? So I actually would not really believe you on that. Okay? Right? Just remember the last time we talked about a joke, right? About an old movie, right? The man actually promised he will give all the money to his wife, do all the housework, take care of the kid, right? And the woman believed him, then they got married, very happy, right? But another scenario, right? If they don't get married, they got miserable, right? So that's make the woman believe, okay, let's get married, right? But once get married, the boy would just say, oh no, I'm not doing anything. I mean, you do all the stuff, okay? Then you become miserable, right? So it's kind of like you cannot keep, it's not dynamic consistency. Cannot keep your promise. I mean, of course, why this story doesn't happen that often, because we have some idea of social contract, your reputation or your parents, right? And the parents actually discipline this kind of behavior, or the law protect this kind of opportunistic behavior, right? Did I answer a question? Okay. So, I think the answer is here. Okay. So the other one is, although we say subgame perfect is good, okay, and it is good for a lot of application, but I would argue that it is not always the best. Okay, this is only a caveat, and this is something like people do experiment on this guy, on this game. Okay, and and this game usually let's look at the game, what's going on. Okay, the game is very similar to the idea that player one decide to stop or continue. Okay, so what the game is, someone put the money on the table. Okay, the first one put the money on the table. If player one say, we start the game, I grab the money, he'll get $1. Okay, and say continue. Okay, that means that another dollar put in the table. Okay, now the player two said, do I need to continue? If he stop, he'll grab the $2. Okay, if you continue, another $2 comes out. Okay, then the player one say stop, he'll get $3, right? He'll get $2 more than the second guy. Okay, and continue, your $2 more drop. Okay, and your player two say stop, he'll get $2 more than player two. And if he didn't stop, okay, another $2 fall down. Okay, and the guy who say stop will get $2 more than the other guy, right? And goes on. If stop, if player two say stop, the other guy will get player two get $2 more. Okay, except for the first round. Okay, otherwise you get $2 more if you say stop. Okay, is that clear? Yes. So the game is so the first round, $1 comes out. Who says stop will get $2 more than opponent. Sequentially. So first one, the $1 there. So you're player one, I'm player two. $1 comes out. You say done, you get the $1. You say continue, and a dollar drops in. Okay, and I say if I grab all I got $2 more than you. Always the one who say grab will grab $2 more than opponent. No, me. It's my turn. First your turn, it's my turn, your turn, my turn, your turn, my turn, your turn, my turn. Because player one say stop, get $1. Player one continue, player two is player two's turn. Player two say stop, I get $2 more than you. And then go continue, I get $2 more than. Is that clear? Is that clear the game? Okay. Of course, you can make it more symmetric, just like start with $2 and then the same thing. Okay. So what do you expect this game? Okay. And the strategy is complicated, right? Because I think I should have 3 more. Okay. I should have actually 3 more. I'm sorry. Okay, because you have to choose S 5 times. Okay, so you can imagine this game is rather complicated, but you have 6 subgame. How can you see such subgame? So look at last one. This is the first subgame, and this is the second subgame, right? And so on and so forth. You go one by one. One is embed over the other. Is that okay? Is that clear? There's this 6 subgame. Okay, I write down everything in case you would. This is the second one. This is the third one. Okay, and this is the fourth one. This is the fifth one. Okay, and the whole game is the 6th one. Okay, 6 subgame. Okay, and you need to figure out each subgame what is the best thing to do, right? The subgame perfect. So you can easily see that because you say stop, you grab $2 more. You always grab, right? You always stop. Is that clear? Oh, right. Sorry. Yeah. You're right. Actually, yeah. You're right. Sorry. Yeah, right. You're right. Sorry. I'm right. Yeah, because player 2 just choose C and yeah. Right. You're right. Yeah. Sorry. Yeah, actually, I'm right. Okay. Sorry. So player 2 look at the last subgame. What he going to do, right? He always grab, right? Because grab is always better than no grabbing, right? Because grab, you get 6. No grab, you get 5. Okay. So go back one stage, or maybe I use the same color. Maybe I use different color, otherwise you may get confused with the last one. So I use this one. This one is this guy. Okay. S. Okay. And now it's player 1's turn. Maybe okay. Player 1 turn. Okay. And player 1, what are you going to do? He compare 5 to 4. Right? So he will do 5. Okay. And then player 2 will compare 4 to 3. Right? He will do 4. And and player 1 compare 3 and 2. He will do you compare this 2. Right? Maybe this is easier for you to see why is the case, right? He compare this and this. He compare this and this one. Maybe I change this one to make it hopefully more clear. Okay. And for player 2, he is actually comparing 2 and 1. He will do 2. Right? That's why I do 2. And player 1 is comparing 0 or 1. He will do 1. Okay. So the unique subgame perfect Nash equilibrium is player 1 see $1, grab. Okay. Is it a reasonable prediction? Unfortunately, this is yes in some scenario. That's why you end up with the case where a jungle, right? Which means that when you see the resources, people just grab it, right? That's actually what happened. The fishing problem. I don't know whether you guys know there's a fishing problem in South China Sea. That's why we have called the fishing recess, right? In every year, there's a 1 month or 2 months is not fishing. Okay. The reason why it's overfishing problem in China is very serious, right? Because in other places you have to make the net big enough so that not catch the small fish, right? But in China or in some other place in the world, people got, very selfish. It doesn't, if they keep going, then it actually can grow more, but you just grab, okay? And you can see there's anything in the middle actually is better than 1, right? And they can't wait, they just grab, okay? They just simply destroy the society in some sense, right? So that's why you need the government to say, okay, no. You are not allowed to choose stop at the beginning. That is what the fish recess is going, right? 休渔期, right? That is meaning that you should wait, not here. Let's stop fishing. Let's continue to somewhere and then we start fishing. Okay, that's what happened. Okay, shouldn't be you shouldn't be allowed to do something selfish, right? So this is actually better, right? Anything here is better than the beginning, right? So that's why you don't allow people to do bad thing at the beginning. Okay. Yes. Oh, sorry, said okay. So player 2, he has to choose 3 times. So he will be the strategy set. Player 2 have to tell one of the strategy. Okay, is he choose S here. He also choose S here. He also choose S there. But also can he choose C, C, C. So there's a 6 company 2 times 2 times 2. 8, right? So that 8 strategy for each players. Okay, is that clear? Okay, so that's the reason why this. Okay, and probably some of you would ask, what would be how real world people play this in the lab? Okay, and interestingly, in the lab, if people can foresee long enough, because in the lab people don't play over the years, right? They play an hour, and if they can foresee there's a good outcome, actually they can wait. Usually you repeat this game. Of course you don't expect here would happen, right? People would do some barrel induction. Okay. At the end, there's somewhere here is the outcome. Somewhere in the middle is the experiment outcome. But do note that because in the lab, people, the discount factor is not very high, right? Because you can just wait and at most several minutes, then you can choose, right? But in the real world, right? From one stage to other can be very long, and people are impatient, right? And just grab, right? And probably sometime you will see. Let me finish this story, and then we have a break, right? You see, in some TikTok, right? There's a short movie saying there's a big lunch buffet. Some people cook free food, very big bowl of food, right? And people go and grab the thing. Everyone has a big bowl, and basically, once they grab, then the thing fall down. No one can eat anything, right? If they waste, I mean, everyone would have something, but they just kind of, I mean, I don't know, end up in that situation. Okay, and that is somehow related to idea what we call the I mean, the market, is it efficient, right? Go back to the first welfare theorem. This idea. Okay, so let's have a break of I don't know, 10 to 15 minutes, 10 minutes, yeah, and then we continue. Okay.
这个 disnotation 是什么意思？
哦，我只是说 player two 你可以选择 S or
这样的这个 notation。
哦，the set 的意思嘛 ，the set。因为我们说均衡的话，就要表达说均衡就是它的 strategy， 所以这个 strategy 跟这个 strategy， 这个是 equilibrium set of equilibrium 的 set 就是用这个 curly bracket， set 就是
我知道 set
x y 就是那个就是3个 element 在这里。
对，我是对里面这个小括号。
哦，因为它你要表达这个 C， 哦，你觉得喜欢你可以就 CG 就可以。
对，这是 CG。
哦，你可以是 CG 就是绝对选择 C 对的。Okay, CG actually means okay, you can write A map to C and B map to G. Because player two 的 strategy function right？
因为我刚才很疑惑，当他选 A 的时候，他怎么？
那我这个 CG 是个 strategy， 所以是这样。
CG 是
strategy。CG 是 A 选择 C B 选择 G。So player two 的 strategy is by different。
But my question is, if A has already choose.
No, that's a strategy. It's equilibrium is in terms of strategy. You're talking about outcome. It could be outcome is if A, okay, if outcome in this case AC, but the strategy is ACG. Of course, this is a simplicity, right? We just saying the strategy is S2 of A is S2. Oh, S1 is A. S1 has no choice, has no choice. Because S1 is depend on the NOV history.
这个是的，就是让我理解 strategy 是一个 strategy 是一个 set。
No strategy, no strategy 是 go back to here, we define strategy. Strategy 就是 what action has to be done. Okay? In this case, what are the actions? All the action has to be taken. Okay? You have to move only the beginning, so that's why the strategy is look at all possible history. And player two have two different histories that you can move. Under A, you have to choose an action, the B is here.
而且 strategy 通过往后的从前往后，
因为 depend on history what is the strategy. When you solve the game, you solve by induction. But the strategy is forward, right? Because the game proceeds accordingly.
那这样这么写的话，按理说它应该是。
No, that is the strategy choice. But this, yeah, it's the two possible strategies. Yeah, the strategy set. Yeah.
但是我的问题是，为什么这个地方不，它这个东西不是 possible strategy， 而这个地方
No, because you have to choose. Well, that is what the meaning. You have to specify all possible history. What is going to choose? That's why.
就是这个东西前面是 history， 然后后面。
No, this is no, same. No. This is strategy of player one.
就需要做 pair， 就等於你猜拳嘛。OK， 猜拳的話你是人家出了什麼，然後你再選。如果你是 sequential 的話，所以你要選擇他出什麼，什麼就 specify 兩個情況。
他们之间有个先后顺序。
对对，相同。因为这个选择 A 的时候，
但问题来说，并不真的是全题。如果他
no， 当然你要 specify， 你一点没有说一个，没有说明这个情况，因为你不说明这个怎么叫这个时候，觉得你不能按对你的问题是 you cannot go unspecified。You cannot go unspecified for this because in order to say this equilibrium, you must tell me what is to do, then to check whether he deviates. The problem is, if you don't write that down, how can you check the deviation?
其实我还对这个 strategy 的 notation 有点。
No, you don't have to write this. You can write this. You can write all possible things. So equilibrium is just bunch of strategies. But the strategy for say player 2 in this case, you have to depend on what all the history has to be. In this case, it's A and B.
那我像这样的一个 strategy， 就是怎么去抵抗它应该被就是它的意思是说A 跟 S 还是在
No, choose A then choose C. Choose B then choose C. 这为什么等价？因为他每个人是不一样的。为什么等价？你在说double gap，
就是假的，就是我的理解，而说法就是后面是一个，但是前面话是一个
No， 第一个也是，
第一个也是，
这是 pair one， 这个 pair one 是 pair。
但是如果根据 strategy 的定义 ，strategy 应该是一个 match。
That is no history. That is no history.
那我他最开始某个东西，来提到他的那个什么错，那么这个东西
也写下了 history。
这个。
因为你要 specify 这个，如果你不 specify 的怎么叫它 ？How can you check what you do？ 因为你要，因为你现在这个 equilibrium 里面，但是你要 check 这个是 feasible， you have to check whether it deviate to this one. That is it. That's why you specify that. Otherwise, you don't know what's going to check. 要不然你怎么做 pair one deviation？
这个定义知道，因为它前面它的
对，一点那个 strategy。Depend on. You have to specify what for all possible things. So that's why I define this way. Make sure you have to write that. What is the game? Yeah. So you have to specify what all the action. Yeah, I should add them back. But I think it's very. I think it's here, but I should write down in the definition. So, but I think it's here. I just didn't write the properly for that. Sorry, I A 个选择 C、D、E，然后第二个 M、E， 因为什么？因为你要，because here you can choose this one or this one。就因为有4个这个 H、H、H、D、strategy 是他们就一个整个 game 的描述，还是某个人的一个描述，就是 I have a strategy。The strategy is say player I said with all his what he can do. So he can do in this不，你是到这边就是生产所有strategy. You cannot say I don't know what to do. I'll be what to do in this scenario. That's what the strategy is. Player one, other strategy is all if you move again. So if this A1 said player one. I don't want to be too mathematical, you know. But no one actually write in that way.
implicitly it's in that way, but no one actually write in that way. Because it's cumbersome, there's no need to do it. Just specify, tell me what to do in every scenario, and it's clear. Okay. I guess some of you actually asked during the break is why the strategy has to have two things for player 2. Okay. One of the reasons is you need to check whether player 1 will deviate. Right? Suppose in this case, player 1 choose A, player 2 choose C and G. Okay. If I just say player 2 choose C, then the player 1 choose A, player 2 choose C, then I'm done. But how can you check whether player 1 is doing the right thing? You check if he deviates to this, what's going to do? You tell me. You cannot just say, I'm not going to tell you what's going on. Okay? So that's why you have to pick what you're going to choose here. Then I can justify this thing, right? You cannot just say, you do that, I forget. No. Okay? You specify very clearly what's going on here. Okay? So that's the reason why for strategy or equilibrium, you have to specify every possible cases what you're going to do. Okay? If not, then you cannot check whether other guy will deviate. Is that clear? Yes. The problem?
Why don't we have the strategy of
ABG? AEG. Oh, because AEG, player 1 actually would choose B, not A. So, so the question is whether AEG is a Nash equilibrium. You say AEG. Why this is not a subgame perfect Nash equilibrium? Okay. The thing is, if player 2 choose E and G, okay, what will be player 1's choice? Is it choosing A reasonable choice? Because A will be, if you choose A, the payoff is 0. B, the payoff is 1. Then this is not the best response. So you will choose this is not. Is that clear?
That is according to the all fast PE AEG has to accept right?
AEG is not subgame perfect equilibrium because A is not smart. Right? Okay. It's okay. So here, I guess now is before. Okay, the first definition. What we have is only one guy move. Okay, in each node. Okay, but here we want to introduce what we call simultaneous move, which means that in some scenario they move together. Okay, that is very important. Is before it's completely I move once and the other guy and take turn. Okay, it's very boring. Okay, but now it's less boring. Is in some situation we move together, and then we know what happened, and then we move again. Okay, so that is very common being done. Okay, and so this is a little bit more complicated. Let's see the example. I think it's easier. Okay, and what we are going to do is to try to tell you how to define a simultaneous matching pennies game. Okay, just together comes out. Okay, how can you define it? Okay, the definition remains the same. Okay, the only thing is the player function is a little bit different. Okay, because now they can move together, so we have to define from now history both of player move together. Okay, they move together. Okay. And the action set, you have to be careful because before it's just only one guy move at one point of time. Now you allow them to move the same time. So you have to specify by agent sub I, okay, sub 1 to 1, 2. So it will be more complicated. Okay. The action set can be more complicated. So that means that the history is more complicated, right? History will depends on what they have possible have been chosen. Okay. So you'll be more clear later. Okay. So the payoff is the same. Okay. So so you can see they move together. How can we represent this in the tree diagram? Because this is the only thing we care, right? For most of the application, we just write, and then we will say we will have a what we call information node or information set. What it said is if you try to, let's see this one, you will use a tested node. Okay. If you encircle it, it means that player 2 actually doesn't know where he is. Okay. Player 1 choose head or tail. Okay. But player 2 doesn't know whether he is in which one. Okay. So that means that 1 and 2 will move together. Okay. And in this expression, player 2 strategy only is just X or T. Okay. The strategy choice is either this or this. Okay. You cannot do this. You cannot do X here, T there. Okay, because he don't know where he is. Okay. So that's how you would write this one. So this is very important. And of course, we solved this model already, right? This model have only unit equilibrium is randomizing the coin, right? So we have shown in the last class. Okay. So let's see this example. I think that's good. What is strategy of player 1? Okay. Player 1, you have to tell me only, okay, in the beginning and here, right? So player 1 actually have how many strategy? It's 3 times 2. Okay. So player 1 can strategy actually consists of, I mean, 2 parts. First is A, B, and C, right? So you have to tell in notation, it means from the null history, what's going to do, right? What possible is A, B, and C, right? That's 3 possible cases, right? But he's also under this thing. He also have to choose. He don't know where he is. He's also maybe I just erase this one. It's easier, right? He will also actually choose F and G. Okay. So this is his strategy choice. Okay. Do note that he don't know where he is. Okay. He's either all F or all G. Okay. And so he can either this one or this one. Okay. He cannot say F here, G there. Okay. If he did, then he know where he is. Player 2, you can see he has 2 strategy here and 3 strategy here, right? So S2, the strategy set is D and E cross product of Hij. Okay. Again, you have 6 strategy. Okay, because you can choose either one there, either one there. Is that clear? Now the problem remains is how do you solve this model? Is look at the subgames. Okay. And again, the whole game is one subgame, right? And what else are the subgame here? Okay. This is the game by itself, right? This is a complete game. You can take it out. You can solve it. Okay. So remember, subgame is just like you solve a smaller game, okay? The smaller, simple situation. And that's our subgame is here. Okay. And your subgame cannot cut off. This is not a subgame. You cannot have this here because if you do this, it means that player one knows where he is, right? Because player one doesn't know where he is, okay? You cannot simply cut it out. So that's why this is not two subgame here. So just only whole thing. Okay. And overall, it's another game, so that's 3. Okay. If you don't have this guy, then you have 2 more, but you don't know where they are. Is that clear how you would be solving this game? You will be, if you find the subgame perfect equilibrium, you have to find what is the optimal action here, right? And then replace the outcome here. And then you solve this game. This is just a simple normal form game. You replace the outcome here, right? Then player one will choose between 3 of the outcome, then pick the optimal action. That would be how you do the barrel induction. Let me repeat the statement. Okay. To solve subgame perfect equilibrium, you can do barrel induction. Barrel induction means that you, in every subgame, you go from the backward, so look at the last subgame. What is the optimal choice for player 2? Okay, you can compare J, L, M, which one's the biggest? Take them. Okay, and look at this subgame. Okay, you want to see whether whether DF or DG or EF or EG is an equilibrium or some mixed strategy, right? Because this is just a normal form game, right? This is what we learned. The table, right? 2 by 2, right? You can just solve this game, and then you replace the equilibrium outcome here and just solve it. Okay, so that's how you solve this game. Is there any question? Of course, we go to application, but this is just ideally how you can solve this kind of problem. Okay. If no question, then let's go to application. Okay. This is again a pretty interesting problem, and what we call the niche choice game. Okay. And now here the difference is once it enters, the entrant can decide which market they focus on. Okay. If they both choose small, then they just die, right? If small and big, then still I think the entrant lost $1. Okay, this incumbent because he too small and large, right? Is 1. And if they both large, they lose much more because they fight a lot, right? If the small focus on small, right? I think he still get $1. Okay, so this is a payoff. And the number is very important, but just see the game. Okay, and look at this game. You have 2 subgame. Okay, 2 subgame. Why? Is this is the first subgame, and this is the second subgame. Okay, so basically what you're going to do is solve this game. This game is simply a normal form game. Okay, what you're going to do is to write down the game. So I write it down in the slide. Okay, I write down in the slide here. Okay, we focus on this subgame. Okay, this is the lower subgame we can focus on, and we just write down in this format. Right, the easiest to solve. Okay, and then you focus on. You will easily see the red one is the best response. Why? If small, okay, I go quickly. 1 is bigger than -6. If large, -1 is bigger than -3, right? And player 2, look at small. 1 is better than -6, and large, -1 better than 3. So these are the 2 outcomes. Okay, you can see this is what we call the anti-coordination game, right? If you're small, I will large. If large, I will be small, right? Because you large and large, then you just hit on and they die, right? Just like the not coordinating, right? Anti-coordination game. Huh? Yeah, just like the chicken. Yeah, it's a chicken game, right? If they hit together, then they die, right? So this is what it has, right? So, and And so what should we do is you just there are two equilibrium here. Okay. You would focus on, you can take one equilibrium up or take this up and then solve the model, right? Because these two are the reasonable outcome from this game. Okay. So that's why either is under large and small, under small and large. So just flip these two, right? So in under the large and small, okay, player one strategy is either out or in, right? And either you choose 0 or 1, right? Clear that you choose 1. So it will be in large and small. Okay, this is player one strategy. This is player two strategy. Okay. And under this case, -1 in, right? So player entrant will choose out. Okay? In this case, it's out, small, and large. Okay. So here you can see, is that okay for this one? And of course, just to remind you, out you have to specify this guy. Okay. Okay. Otherwise, you don't know why it's out. Right? When you choose in, actually that will be he will choose small and large. Okay. So from this one, there's actually a very interesting phenomenon you can see in this one. It's actually you can see when you introduce a more details here. Okay, out can be a subgame perfect equilibrium, which is not there in the previous setting. Okay, so it does mean that if you don't get what you want, okay, probably is you are not modeling right, or you don't model the details. You have to model more details, probably you get what you want, right? Because you try to make a model, the model doesn't deliver the outcome you're expecting. It's highly likely that you are too simplified, right? If you try to model one more thing, okay, when they come in, they're actually playing a competition game, okay, then it's okay, right? Because now it's clear. Okay. Okay. Is that okay? Okay. I guess I will, after this example, then I think I will give you a break. I think this will be then, because then we'll talk about repeated game. Okay. So this is stackable competition is something that you learn, I guess, in your intermediate class. Okay. But we will learn it in a game theory setup. Okay. So everything become a game theory idea. Okay. So don't worry about the subgame thing. I mean, you probably would be nervous to see this kind of stuff and how many things you count. But usually the strategy is continuous for most of the case. So it becomes a calculus problem. So that one you know how to solve pretty fairly easily. It's not something that you don't know. You know very well. So you can see the cycle outcome. You see the similarity here. Okay. So this is just a Carnot game, but one firm move first. Okay. The question probably is why that firm move first, right? But I mean, we can solve this game, right, quickly. But why this firm move first? Any reason why the firm move first? Anyone can tell me why one firm move first?
There is always a firm move first.
Yeah, but why people wait for him to move first? Why is a reasonable model? Why don't we model a Carnot? When, okay, this is a good question, right? Why you would think a particular firm will move first? Why? I mean, there's any reason why. So suppose, right, you already know, we don't game theory, right? The question is, in practice, right? Why you would model this timing, right? The referee usually write a model, you send to the journal, referee will ask, okay, if this model is not written by others, you invent the game, he'll ask, why this thing move first, right? Usually the answer to yourself is, okay, this is the only model I can solve, the other way doesn't work, okay? That's right, okay? That's something like this, but you probably have to answer why this makes sense, right? Why this will make sense, okay? And the answer is, okay, one way to justify this is the firm that moves first usually is very big. Okay, a big firm has market power. So basically, it's like big oil company or big. Look at Hong Kong bank industry. Okay, I don't know whether you know the finance, but Hong Kong, which is the biggest bank in Hong Kong? Hong Kong Bank, HSBC, right? They call Hong Kong Bank, right? But yes, but HSBC, I mean the local people call Hong Kong Bank, but anyway, but Hong Kong and Shanghai, HSBC. But at Hong Kong and HSBC, he set the interest rate, right? Everyone would follow. The reason why it's big enough, he set the price there, everyone just simply follow that price. And even the reason is why he moved first, even though he moved later, actually people will follow. It doesn't mean that he actually moved first, doesn't really matter. It's people will look at him and follow. That's actually what is going on there, right? Because it's big enough, he has market power, he do it and you just follow is the easiest thing, and that is what happened. Like the oil industry, right? The OPEC is big enough. Whenever they decide the quantity, other may just follow, right? Because you are fringe enough to the market for the other player. So basically the first mover are the big firm or the major player. Others are fringe players, right? So look at the finance, right? Because I know more. Is right. Look at Warren Buffett, right? He try to do things, then a lot of people follow. Or the big fund manager, right? When do things, people just follow, right? You can imagine like the big investor, right? Move first. Other people just simply follow. So this is how you explain. But as I said here, right? And the referee will definitely ask you if you set the game in a particular way, right? They will ask you whether your model is sensitive to your timing. Okay. Usually, if you're lucky, usually your model will work if you change the timing. The old equilibrium will still there, but you have something new. That's okay. But the problem would be if you change the order, the timing, your equilibrium gone, then you have to spend your time to argue why this is correct. Okay? Which is okay, I mean, but referee definitely ask, okay, these days. And particularly the trading model, you look at finance, people will just move, okay? But say in terms of marketing, although is marketing here? Marketing? No marketing, right? But usually no marketing student, that's good. You're marketing, okay? Marketing student, then you will usually it's easy. It's because usually you make firm move first and consumer move second, right? Rather than consumer move first, firm move second, right? Or you can assume a supply chain, right? The upstream move first, and the producer, and the wholesaler and the retailer move along, right? But when the firm is big, say the Apple is the middle guy, right? He can move first, and everything move, right? You look at the price, right? When Apple decide the price, and everything move, right? The downstream, upstream, or the semiconductor, right? When they raise the price, right? And everything on the downstream move, right? And so it really depends on how you model it, okay? And of course, this is something not usually set in the textbook, but you have to be very careful how you set the time. But in the text, in the exam, or in the assignment, or the textbook, you will be told who move first, who move second, right? You have to think carefully who move first, right? It is possible that the fringe market, the small firm move first, right? Because they are very quick to move, right? And then the big firm will move later. Okay. So in some games, the first mover has advantage. So in Sequential game, you will see the first mover advantage there. But in some game, second mover advantage, right? Like the sequential penny matching, right? Move second is better. So you can easily think that which one move first and second depend on application, right? It's not just the stronger guy move first. Okay, I hope that is clear. Right, so that is that is what happened, right? I mean, that is also what happened, right? In the nature, in animal world, right? And some animal, the female animal looks very pretty, right? And hoping to get a mate, right? But in some animal, like孔雀, right? It's the male who is more beautiful, right? So it depends on the situation, right? Anyway, so now settle back game. Go back to here is we have one firm move first. We argue why he can be the first mover. Okay, it's the same game, right? We have we have a linear demand curve, right? Constant marginal cost, okay? A standard profit. I don't think I need to describe it. And firm is first mover, okay? So that means that the firm one is very simple. The strategy just decide how much output it's going to choose. Okay? But it becomes more complicated for the firm two. Firm two is going to make the production choice after firm one is being done. Okay, here you can see there's a time dimension here. Okay, it can be actually the time that happened because firm one is actually the first producer. Firm two is the one who the new entrant. So this order will make sense, right? Maybe the firm first come into the market, so he moved first, right? Anyway, so the key here is the strategy of firm two is a function. Okay, depend on what firm one has chosen. Okay, so that's why it's firm one's choice to firm two. Okay, so in general, this is very difficult because you specify every single action, right? But turn out to be this is a simple function. Okay, so that is the main thing. So let's actually do this. Okay, and how can we solve this model? Okay, the way to do it is simply doing a bell induction. Okay, you assume firm one will produce this much. Okay, this is a unknown. Okay, with Q1. We assume Q1. So basically, firm two is solving this problem. Okay, maximizing the profit. Consider the Q1 is exogenous fix. Okay, that is the way we solve. It's same as we solve the best response. We keep Q1 as a constant. Okay, because why do it is because of under a certain subgame, Q1 is being chosen. Okay, so what it's doing here is like this. Here we are solving a particular subgame. So look at this. L1, okay, that's how usually you write, but so usually this is how you write when you do a continuous one. Q1, okay, Q1 actually running from 0 to A, right? I mean, of course you can go to infinity, but you never post more than A, right? But you can just and then Q2 is choosing again 0 to A. Of course you can no need to A, you can just get more is fine. Q2. Okay. And this game, the payoff, right? Those payoff will be just A minus Q1 minus Q2 minus C2 Q2. Right? So this is the payoff. Is that okay? This is the price, right? Okay, this is profit margin. Okay. So this is what is saying that in a particular subgame, this is the outcome. The good thing is we don't need to solve every possible subgame, right? Because every game have the same structure as this one. So that is make the thing easier because every subgame actually is the problem parameterized by Q1. Right? So do note that we are not solving one subgame. We are solving infinite many subgame there. Because for every Q1, we have the same scenario depending on Q1, right? So that's why it makes our life easier. Okay, it's different from do look that it is the same thing, okay? But it's a little bit different from previous cases because we are solving the best response for all possible subgame. Okay, all possible choices of Q1. Okay, and turn out to be it's very simple. I can usually solve it, right? It's just 1 minus Q1 over. This one is okay, right? I don't need to derive this, right? I think you do the assignment, you know this one, right? The same Carnot. Okay. Is that okay for this one? So if Q1 produce 0, I have A minus over 2, right? So this is exactly the same as what we learned in the. There's no different from the thing we do in the previous class, right? It's Q1. This is Q2. Right? If you still remember this one, right? If Q1 choose nothing, what is Q2? Is A minus C over 2, right? And if Q1 choose A minus C, what's Q1? So if Q1 is A minus C, maybe I draw it lower to be let me draw it lower. Right? It's this one. Right? This is the best response for player 2 given Q1. Okay. This is exactly the same as what you learned last class, right? The Carnot, right? Because that is hypothetically what Q1 is choosing, what beta, what firm 2 is choosing. Okay. Is that okay for this one? Now we are doing barrel induction. Okay. So in some sense, is player 1 is actually choosing along this line. Right? Because when player 1 chooses this, player 2 chooses here. Okay? So player 1 is basically choosing an outcome along the best response of player 1. Oh, I should be a little bit more careful. I forgot to write this one. Anyway, same thing. Okay. So, and anyway, do I need that? Oh, sorry, this one. Sorry. Oh, I mean this guy. Right. Okay. Right. So so basically, firm 1 is choosing any point here or there. Right. So any point would be good. Okay, because if player 1 chooses here, then player 2 chooses, all right? So there's basically picking which is the best one. Okay. So how can you solve this problem? Very simple, right? You just plug in this equation into here. Or player 2 do it. Okay. So what is barrel induction? It's simply that player 2 will just put the best response. Okay. It's a barrel induction, right? Because you would be assuming if you choose this much, player 2 would respond in that way, right? So that's why Q2 is not a exogenous for Q1. Okay. Production of firm 2 is not exogenous. Okay, so that's different. Is that clear? Because this is supposed to be Q2, right? But this Q2 is not going to be fixed because firm 1 depends on what is producing, firm 2 will change. because firm 2 moves later. So that's why you have to figure out, because as I said, you're actually choosing this line. So that's why it's here. Because this is Q2, right? So that's why when you plug that in, right? When you solve it, okay, turn out, right? The best point is being here. Right? We choose this guy. This is the profit is highest in the middle, right? If you look at, if you think profit is this is toward us, right? Just like, okay. And this is the best outcome, okay? And then you can now, this is the, so you can write the equilibrium, right? The equilibrium, okay? I have to be careful here, write down. So equilibrium in this case, okay? If you have to be careful, equilibrium, the strategy of player 1 is A over C, okay? S1. Strategy of player 2, equilibrium strategy, is A minus Q1 minus C over 2. Okay. Remember the strategy, this is the equilibrium strategy. But that's a subgame perfect equilibrium. Okay. But of course, we do tell this is not the outcome. The outcome you have to put A over C in here. That gives you A over A minus C over 4. Just put in there. Okay. So this is the outcome. Is that clear? So this is this 2 is the subgame equilibrium outcome. This is the subgame perfect equilibrium. Okay. To be careful, you have to distinguish, right? The equilibrium is a strategy. It doesn't include any outcome, just strategy, right? Just tell me, player 1 choose this, player 2, what's my strategy? I will just A minus the quantity 1 minus C over 2. That's it. Okay. This is the equilibrium. Okay. Equilibrium is strategy. And outcome is an outcome. Okay. And I repeat why we need to define this is because we need to check whether he B.B.A is to tell them how he responds. Okay. Is that clear? I guess it's a time of break. And after the break, we talk about with the game. Okay. I think you already learned this. Okay. And before break, I just want to emphasize one thing is here, I focus on the case where only one guy move first and move second, right? And very often there are many scenarios that they would pay simultaneous move game 2 times, right? Maybe you can consider the case, a very famous game worth mentioning is in the first stage, firm competing to simultaneously decide how big the factory they are. Okay, they invest in K, then they can produce K in the next period. Okay, up to K. And the second stage, they compete in the price. They compete in per time. Okay, and this game is can justify why you cannot. Let me repeat the statement. Can I erase this one? Okay. So the game is called the following. First, the 2 firm invest 2K simultaneously. Okay, and each unit of K, then you have to pay cost of CK. Okay, and if you produce K, then in the next stage, you engage in price competition, like Bertrand. Okay, but how much you can sell is limited by K. Okay, so if you invest in 10 unit production, okay, you cannot sell at most you can sell 10. Is that clear? So, I mean, of course, I omit many details, but this game is very famous. It's for showing that why I need the capacity here is because Bertrand, remember Bertrand is you get everything, right? If you know, in the Bertrand model is the one who have lowest price will get the whole market, right? But when we have capacity, you cannot have the whole market, right? You can only have the market up to your capacity. Is that clear? So if you have this model, this can justify the model outcome will be same under some situation, is same as Carnot. Okay, so that's why that's the one reason why you're thinking about Carnot. Okay, although Carnot compete in quantity, but indeed it's not. Indeed, it's a reduced form, a more complicated model. First, firm decide how much to invest in the factory. For each unit, maybe for each unit, the marginal cost is C. Okay, it's easy, right? And in the second stage, once everyone compete in their capacity, then they engage in the price competition, like Bertrand. The lowest price get everything up to your capacity, right? You cannot produce more than your capacity, right? And in that case, okay, you can generate the outcome as you observe in Bertrand, right? In the beginning, you decide how many K. This outcome is a Bertrand outcome. So that's why you are considering quantity competition. Indeed, is actually competing in production capacity. Okay, and that has a, of course, there are many justifications for Carnot, right? Because in the real world, except oil industry, right, or some industry, most of industry actually engaging in price competition rather than quantity, right? What they think is they think about the price rather than quantity, right? But in oil, actually they compete in quantity, right? Or you look at the wet market, right? The vegetable, they compete in quantity, right? But in other most of other scenarios, they compete in price, right? Anyway, I guess I have a break of 10 minutes, then we can come back for the repeat the game. 对对，但是你没有，就是有花钱嘛，但是你今天你没有钱赚，可以啊，可以啊，对，那最后就变成款了。
没有写，有没有看到我？对，我问嘛，中队答这个5分，然后一个，然后发现了，有一部分会问我的问题，会问我，会问我，所以嘛，这个 final answer，你们中间答案就在他们给你们就好了，好吧？3个，2个都是。
Hi. Yep. So I hope this one would give you all the tools that you need to write your paper, because actually, as I said, many of my paper actually focus on complete information setup. Dynamic game already can satisfy a lot of the phenomenon you want to describe. Okay. And only if you think information is crucial for your decision, and then that would be interesting to add information, because next class we talk about information. Then you will see the model is expanding exponentially. Then it's very difficult to manage already. It will become very difficult to manage. Okay, but for some people who like challenges, then probably you want to talk about incomplete information. But as I said, if you do with the repeated game already out of this class, then probably you would already have most of things we want. Okay. So this is some summary. Here is like people take action at different point of time. So it's important your strategy is based on history. Okay. So to characterize equilibrium, you have to specify all possible history. Okay. Repeat once more. The strategy has to be specified for all possible history. Okay. That means that every decision note, you have to tell what happened. Okay. And as we argued many times already, a normal net equilibrium is not a good one, because it's inconsistent, what we call time inconsistency. It's based on empty thread. It's based on the fact that if you actually go there, you cannot, right? And actually, there's some, in some sense, okay, that's the reason what we call commitment is important, right? Because remember the very beginning, actually, there's a commitment is a very important topic in game theory anyway, but we don't go ahead or go that far. But if you consider this case, right, if the incumbent, okay, can commit to fight, okay, then probably they stay out, right? Say what happened in the Russia and Ukraine, right? Russia want to claim, if I'm attacked, I will nuclear bomb everyone, right? But is it going to be credible, right? And obviously not, right? Just they get out, right, from what they're supposed to be, right? I mean, they commit, right? They commit by annexing the region, right? Because by the constitution of Russia, right, no one can surrender the land, right? They try to commit, but not successful, right? I mean, unless Russia is willing to throw a bomb, nuclear bomb, then probably it's okay. But it's not clear they would, right? And they try different way to manipulate, try to make the other guy believe it's a good thing, right? So that's why in that case, information is important, right? Because I don't know how crazy you are, or I don't know how serious you are, right? So that's why we do so many things, try to convince other people that's credible. That's something we like, right? And that's what happened, right? What happened to sending flowers to girls when boys send for the girl? It's completely useless, right? No one eat the flower. The flower has no value, right? The reason why the flower is useful is to send that, okay, even though it's useless, even though it's costly, you try to send that, you try to send a message to the girl, okay, I'm serious, right? And you buy useless thing, right? And to the girl, right? Why? Try to show a signal is being serious, right? And in so also in some case, right? I don't know whether some part in China, okay, when two guys fight, okay, I don't know, maybe Dongbei is northeast, okay, I don't know the Dongbei people, Dongbei people, no Dongbei, right? Anyone Dongbei? No, okay. When two guys fight, okay, and what they do is one guy will just have a knife, cut himself first, and then fight. Why? Right? It's crazy, right? You just also like the gorilla when they fight you. Why? Why hit yourself? Right? It's crazy, right? Why? Because by hitting yourself, you mean I'm very strong. I cut yourself, I mean I'm very brave. Okay? It's showing that if you ever come to fight with me, I will just not stop. Right? So that's the reason. Okay? So actually that is underlie what we're doing for the next two topics is like information. The last game is like signaling. Those kind of things is very important. Okay? You try to signal, you try to do things, try to influence other guys, think that you are strong. But anyway, that's what we left for the very last topic. Okay. And also, yeah, maybe I just go to the video game. I don't want to stay for too long. Okay. So video game, although this is a special type of dynamic game, okay, and this is I think somewhat important, okay, and to explain a lot of collaboration or collusion would happen, okay. And in this literature, actually turned out to be there are two important distinctions, is whether the game repeat finitely or repeat infinitely, okay. And going to infinite actually gives you very different result from finite, okay. So you can see a lot of model when they repeat it, then they will distinguish whether it's finite, infinite, okay. You may expect when you repeat finite number of times, when it go to infinity, okay, is it going to be there? Okay. Usually, I mean, is the case is, I think in general in game theory, the idea is like this: is if you try to take things from finite to infinite, usually things should still hold. Okay, but when you go to infinity, the number of equilibrium may expand. Is that clear? So if you try to, so if you take some parameter n, okay, maybe this is a strategy that's equilibrium strategy, okay, continuous function, right? Maybe when n's number of repeat time may be originally like this is equilibrium, okay. When you go to infinity, become everything is equilibrium, or a lot of things equilibrium, okay. So it means that the when you go to infinity, the thing become very different, okay. But the original model is still equilibrium, okay. And one of the results turn out to be when you repeat the game many times, there will be one result called Fock theorem. The Fock theorem said the following: basically, anything is possible. So basically, say nothing.
What's the
Fock theorem. Fock theorem. Fock. Fock theorem is if people are patient, okay, anything is possible. Okay. So we'll talk about that very quickly, okay? Soon, okay? So let's consider this one, okay? And in repeated game, this is usually the only game they study because this is easiest enough to study what's going on, okay? Of course, you can generalize to more important cases, but this is, even in research, this is the game that they will study, okay? Even in theory research. So this is the game that most important one. Okay? So I guess there's no need to repeat. If you play this game once, okay, only defect, right? Or right, there's only outcome. And suppose to play twice, what happened? What we expect? The answer, it is still 2 times of defect, barbaric induction. Why? Because the last stage, there's only one Nash equilibrium, which is defect and defect. Okay, maybe I just draw it here. What's going on? Okay. So the game has 2 stages. First stage is present dynamic. Second stage also present dynamic again. Okay. So do note that the strategy in this game is a little bit more complicated because each player would have 4 strategies. Why? Because of 2 in the first stage. Oh, actually not 2. It's way more than 2. Okay. You have X strategy, right? Because of the outcome of first stage is collaborate, defect, collaborate, defect, right? For each history, you have to say what they're going to do. Okay, so that means that this game is like in the first stage, everyone is either choose C and D, right? And here, the strategy is you have to tell me, say player 1, you tell me in the first one is C and C, what's going to do? Player 1 also, all the 4 possible case. So 2 times 4 is 8. So everyone X strategy. Is that clear? And let me repeat once more because I want to make sure it's clear. Okay. So for the strategy in this model, in the first round, the strategy is simple because there's no history. So that's why it's only C and D for each single guy. Okay? But for the second stage, it's very complicated. The reason is your strategy can depend on what happened in the past. Not only your choice, but your opponent's choice. So in the first stage, there are 4 outcomes. Then for each 4 outcomes, you need to tell me what's going on. Okay, maybe I draw a diagram here. So it will be player 1 can choose C and D. Player 2 can choose C and D as well. But this is here. Right? Now player 1 move again. And he will have C and D here. And player 2 will have C and D. Okay, that's the same. So player 1, right, you can see the choice is here once. Right? So 2, 2, 2, 2, 2. Is that clear? So that's why 2 times 2 times 2 times. Okay? Oh, sorry, it's not 8, it's 2 to the power 4, sorry. How many strategy here? Right. Yeah. Okay? It's, oh, no. 2. Yeah, right. It's 2 to the power 4. 2 to the power 4. That's right. Yeah. So, but it doesn't really matter the outcome. The reason is, look at the subgame here, right? The subgame here. This is a subgame, right? And this subgame, we know how to solve it. It's always defect, right? So you go back to here, right? And because this doesn't affect what's going on here, right? So you can just analyze this alone, right? So same outcome would you get, okay? So if you really want, you can just see, you will see that if you repeat this game, no matter how many times you repeat, it's always the same outcome, okay? So that actually the theorem behind is, if a stage game, which you repeat many times, okay, this game has unique equilibrium, okay? No matter how many times you repeat, you only have this equilibrium. Is that clear? Because barrel induction. Because last game you solve in this way, and repeated game means that the early stage doesn't affect what is the payoff in the next stage, right? You only affect what the strategy, not affect the game. So that's why you can analyze the same, right? So each game would be the same. Is that clear? Is that clear? Okay. So now this is actually the game theory problem, and the game is always asking the problem under different setup. In this, the simplest case is, if we repeat this many times, can we support this one? Can support CC, which is a better outcome, right? CC is Pareto efficient, but it's not net equilibrium. Okay, and this is a central research question in game theory. Sorry, in repeated game literature, is we add, say, suppose we add incomplete information, we add a lot of crazy thing, there will this CC will still hold. Okay, so this is the game. This is essential to the development of game theory. Still now we don't fully understand what's going on. Okay, if you add incomplete information, you don't know what happened in the past, imperfect play, imperfect memory, that many things can add. And this is still the game that people still study, not surprisingly. Okay. And because the simplest you can understand. Why this game is so good? Because there's a conflict of interest, right? People want to deviate, and then we see whether we can collaborate. Okay. And now we repeat infinitely. Okay. And we ask, is it can we support this outcome? Okay. And when we say this, okay, so we have to, the easiest thing to generate the support is what we call the trigger strategy. Okay. The trigger strategy is we assume the player will maintain at a good outcome. Okay. Once any deviation, okay, you will go to the worst Nash equilibrium forever. That's called Nash reversion. Okay. You will put the punishment forever. Okay. Just like if a man have affairs, the woman will never forgive him the divorce. That's it. There's no buyback. Okay. 不回收了. So that is what it means. Okay. So that's what it means. Okay. So what it means is, if the first round people try to be collaborate, okay, and if there any sign of no collaboration in the past, that will be forever. Okay. So basically, it's like we assume the heaven, and if that's not in heaven, go to hell forever. Okay. So this is the worst thing you can punish in some way in this game. Okay. So how can we support this strategy? Okay. To look at this is complicated, right? Because it's saying that C in the beginning or CC have been paid, it's going to CC, right? So it's what it means is the following. So what he said is the strategy is, if initial is nothing, okay, if all the CC in the past, CC or CC, the history, right? Then you choose C. Otherwise, you choose D. So this is strategy. Okay. Remember, the strategy is very complicated. You have to tell us what happened in all the history. Okay. So that's why you can see the math. You will never try to write down this kind of stuff. You rather use the English. Okay. I mean, of course, you still can write down your math, but you can see the math can be very cumbersome. So that's why I'm being lazy to write down this way. Okay. But I think it's very clear. Okay. And how can you check this is a subgame perfect? Okay. First, you have to check whether it's Nash equilibrium first. Okay. And we'll show you this, and I will try to check whether subgame perfect. Okay. First, we try to check this is a Nash equilibrium. How can you check? Okay. First, we will define. Oh, the typo here. How can we check is typo here? What's the payoff following this strategy? Okay, Nash equilibrium is, according to this strategy, what's the payoff? Okay. If we follow this strategy, each period, no one deviate. The left-hand side is everyone get 4. Right? Everyone get 4 for every period. And every period discount by delta, right? First period get 4, the second period delta 4, so on and so forth. Is that clear? This is 4 for every period. We do time discounting, okay? And this is one way to do it. And okay, usually we assume delta less than 1, okay? Need not be, but delta less than or equal to 1, okay? And the reason why we have to assume delta less than 1, because if infinite sum, you cannot compare to infinite in most cases. Okay. So and if you deviate from that, okay, what is deviation? The deviation is once you deviate from the equilibrium, you get 5, right? You're being optimistic. But afterward, everyone will go to hell, 1 forever. So you get 5 and get 1 forever. Okay? You need to make sure that this what happened, right? If you this is just geometric sequence, right? 4 over lambda, 5 delta lambda, right? And 4 is 3, right? And then just you get 1/4. Okay. So that means that if players are discounting the future more than delta, you can support in Nash equilibrium. Okay, no one deviate. So this is only checking the Nash equilibrium. Okay, it's not subgame. It's not. We do not yet check subgame perfect yet. Okay, because only what we are checking is checking this null strategy. Okay, what we're checking is we are just changing. Okay, at the beginning. Okay, because why you only need to check this, right? Because initially you can either C or D, right? You change to D, regardless of what we choose, the future is the same. Okay, suppose the other guy is trigger strategy. You no matter what strategy you choose, okay, if you not all the C, is if you choose the D, the first guy, like this. Right? If you choose C in the end period and then D, the same thing would happen. Is that clear why this is true? Let me repeat. Okay. Your strategy like this, right? Your opponent like this. Okay. So what you are going to see is, okay, either you would choose first period, choose D, right? And then so on, you choose different thing, right? If you do this, this will happen, right? Because you can only have 5 and 1 forever, right? But if say the first period choose C, and then you say you choose D later, okay? Then the first period is the same, you get 4, so you can cancel out. You have the same equation there. Is that clear? So that's why this already check all possible strategy. Is that clear? Okay, because you need to check all possible deviation at the beginning, right? Is that clear? I mean, although I write in this way, actually I check all the strategy. Okay, be very careful. Okay, because the structure is the same, right? So if you do this, actually what you do is 4 plus 4 delta da 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 da, right? It's more than 4 plus 5 delta 1 delta square, so on and so forth. So if you only deviate the second stage, the first stage is the same, so you can take it out. You delta, the same thing. Let me repeat, okay? This is considering the case you would just being mean in the first round. Suppose you are good, you're nice in the first round, but mean in the second round, right? The first one, you get the same payoff. The second one onwards, same as this one. But you have delta 1 more, right? The same thing, right? So that's why this already check all possible strategy. Is that clear? It is not, we don't write just once, but I have actually, because of the structure of the problem, I actually check all possible deviation. Is that clear? Maybe I should write down in here, but actually there's a very complicated thing in behind, okay? Okay? Although I just do only one strategy, right? I only deviate once, but actually, no matter which period I start to deviate, the same thing. Okay? Now, how can we check subgame perfect? Okay? What is the difference between subgame perfect and Nash? Is you have to check all possible scenario. Okay, what means that you have to check, given the history, what we're going to do, right? So if it had been CC, okay, it will not deviate, same as before, right? Because what have been done, you're done, right? So actually, the history will start at the same. If it had been CC, the game like the beginning, right? And we saw in the beginning you don't want to deviate. So here, is that clear? The logic. Because subgame is the game proceed is CCCC, right? Subgame means we forget about the history. Now continue to count to calculation, right? But what have been happened has no impact on our strategy, right? If it had been CC, it's same as beginning, right? So that's why same. Is that okay? And then for any strategy, so for any history that's not CC, okay, then everyone is supposed to pay D. Okay, and if your opponent is going to pay D, then you pay D. Right? So there's no way you can forgive. Okay, there's no way you can escape from the hell in some sense, right? You are in the DD region, then you are DD region. Is that clear? The reason why we need to check this is because we need to make sure that this is meaningful, right? This is meaningful, right? But this only along the equilibrium, right? But you never see DD in the reality, right? But subgame perfect will require you to check, is it right that people will pay DD, right? When they actually in the hell, right? Will anyone have intention to escape from DD, right? And we check no, right? Because DD, if other people pay D, you pay D. Even though you are going to repeat a lot of time, right? There's no way you can forgive in this simple model, okay? And of course, in this simple model, once in the punishment, you will forever punishment, right? But you can imagine talking about cartel, you will punish him for some time, then you may forgive him, right? Just like you teach a kid or your boyfriend, girlfriend, right? If he or she or the kid misbehave, you will just a cold war for a week and then forgive, right? Unless you really want to break up, then break up, right? Otherwise, you will just take some time off, right? Same idea. Okay. But in this game, it's so simple. If you break up, then you break up. Okay, no turning back. Maybe allow me to talk about this before I end. It's okay. Just a few more minutes. I finish this slide and then we're done. Okay. So this trying to do is here forgetting B. This is a present dilemma. Okay. What I want to show is okay. If I have a little bit more complicated outcome, okay, and probably is irrelevant, okay, but this irrelevance can somewhat escape the DD hell, okay. Now consider we have an outcome B.B, okay, and this is 0, this is 3, okay, so this is actually inferior to this one, and you can check B.B is a Nash equilibrium, right? Can you see B.B is in Nash equilibrium because right, this is mutual best response, right? B when player 2 choose B, okay, player 1 choose B, right? And when player 2 choose B, so player 1 choose B, player 2 also choose B, okay? So B.B is a mutual best response, okay? And you can see all others are not, right? So what you can see in this game, you have two Nash equilibrium. One is DD, one is B.B, right? And the question is, can we support CC in the first round? right? Because by parallel induction, you know you must have B.B. and D.D. at the last round, right? If you just play this once, the outcome you will predict is either B.B. or D.D. Okay, although B.B. Pareto dominate this one, okay, you don't know which one will come out, right? So the question is, can we support the better outcome, which is not Pareto efficient? Okay, the answer is just like the carrot and stick. Okay, the idea is in the first round, if we have a good outcome, then we go to carrot. If not, then we go to stick. Okay, that's how we support it. Okay, let me repeat the statement before we go to analysis. Is there's a subgame perfectness equilibrium such that in the first round they pay a CC, which is not equilibrium outcome. Okay, how can you support this outcome in a finite repeated game? Okay, is you go to this one. If this can play, if not, go to here. Okay, here I just played twice. Okay, I just played twice. There's no infinite repeated game. Just play 2 times. Okay, and okay, the idea is following, right? If we follow equilibrium, we got 4 and 3. All right, we get 4 and 3. If I follow equilibrium, everyone get 4 and 3, which is 7. Okay, if you try to be selfish, you get 5 in the beginning, but you get punished by 1, so you get 6. Okay, I don't do discount, but you can easily see discount. We also get the same idea if the discount factor is large enough. Okay, so that means that, okay, if what is showing this is if your stage game has more than 1 equilibrium, you can support things is not equilibrium in the first round, in the earlier round. Okay, so that means that your strategy, your outcome can be very complicated, even though the first round is not a less equilibrium, right, which is CC. But as long as you have something like punishment or some support, reward, right, you can support something that is not feasible in the first round, right? So that's what happened in the society, right? That's why you need government, right? Government actually, or social contract or the rule will say, if things goes right, you got reward, otherwise you get punishment. So we can be not so selfish in the beginning, right? So just like, that's why in some society, it take a long time. Then they have a custom that people tend to be altruistic, right? And you try to say if that's why they try to be altruistic. Okay, in that case, they can support this good outcome, right? People try to give and take to each other, right? Rather than being very selfish, right? So that's why you see the outcome is very nice here, right? Why people are nice to each other, right? Say suppose you go to, I don't know, here is a different culture. It's like in the US, right? They open a door for you, right? If you come out, people open a door for you. And if you carry heavy bag, they pick you up, right? And also if old man fall down on the street, you are not be afraid to pick him up, right? But in some country, you don't want to touch him, right? If you try to help him, then you got punished, right? Because like this, right? So, that is the reason why, in some culture, right? You have this kind of thing, then you're okay, right? But if the court doesn't appreciate, then every time you don't have this outcome, right? Then you have a problem. Okay. So anyway, I'm gonna stop. Sorry, overrun a little bit, and I will yeah. Do you want assignment, or just wait one more week? Wait one more week. Okay, wait one more. I can wait. Give you because we play the game. Okay. Yes. Wait 1 more week. Okay, wait 1 more week. It's fine. But I try to release, and you don't have. I still give 3 weeks to do it.